morning. Thank you for coming to this talk at 9:15 on day 2. I appreciate it. My name is Pruett. This is going to be a really exciting talk, because I'm totally losing my voice. So please bear with me as I attempt to make it through this. This is a talk called Lessons from the Front Lines, and what I want to talk about today is lessons we've learned in sort of VR design practices from real product shipping to real customers. To give you a little bit of background, my title at Oculus is Head of Development Engineering for Mobile. But in English, what that means is I'm a developer and I work with folks like yourselves to make the stuff that ships on our platform as good as it can be, whether that's code optimization or design improvement or whatever it is that you need. So I'm here today to talk to you about sort of the things that we at Oculus have learned about VR design by looking at the stuff that you guys have shipped. We're going to talk about VR design, we're going to talk about motion controls, there's a little bit of positional tracking information and stuff in here. This is not a VR 101 talk. I'm not really going to talk about how VR works. I'm not going to talk about the basic principles of VR design. Those resources are available to you everywhere. You can go out and have a good time, and it'll be great. What I want to talk about is second order, third order, sort of iterative design stuff. Also, this talk is a fire hose. I got a whole lot I want to say, and I'm going to attempt to say it. So please use this talk as a sort of broad swath of ideas, rather than a deep dive into any particular topic. Okay, so I said it's not about VR 101, but I actually do want to do a really quick review, like when you're in school. Just to talk about the very basic core elements of VR design, so that we can discuss them, with respect to the new stuff. And I apologize for sounding like a supervillain today. This is awesome. Okay, so what do you need to do VR? Well, you need a headset that has low latency, head tracking, and can shoot photons into your eyes, describing the direction that you're looking at, like a really high frame rate. Sure. Okay, fine. There's a lot of headsets out there that can do this. This is a baseline requirement. Once you have a headset that can do those things, the next problem is all software. How do you design your software to make it actually good? And the main VR design problem that people are trying to solve is vection. Vection is the feeling of, sometimes you call it VR sickness or simulator sickness or motion sickness. It's a feeling that when your eyes and your ears, your inner ears or your vestibular system keeps you balanced. Those two systems are not agreeing, your brain doesn't know what to do, and decides that you should probably feel sick. You can, of course, produce this feeling outside of VR, like if you ever stood on a train platform and watched a train pull in and it kind of felt like you were moving and the train was standing still, that's vection. Or if you read in a car, and if you're the type of person who gets sick while reading in a car, that's vection. Your eyes are saying, I'm not moving, and your ears are saying, no, I'm totally moving. And there's a disagreement there. So the high-level approach that we've seen folks use for avoiding vection very, very generally is that you want to avoid moving camera with acceleration or any kind of nonlinear velocity, no ease in, no ease out, no rotation. And the reason is, your vestibular system can only feel acceleration, right? It can only feel when you move your head in a way that requires acceleration. It can't actually feel linear motion. You can't move the camera separate from the player's head. Like in a traditional video game, it's very common to take the camera and animate it through some nice little spline path or something, but you can't do that in VR. The camera's attached to the player's head and it has to stay there. And the moment you lock it or move it or animate it some other way, you're going to make people feel bad. You also need to limit, if you can, pixel flow in the peripheral vision. And this is because your brain's actually pretty smart. If it doesn't have information from your vestibular system, it'll start to look to other systems to try to figure out if you're moving and how quickly you're moving. And one of those systems it uses is motion flow in your peripheral vision to compute acceleration. So if you can sort of block that out somehow, you can improve the feeling of motion for certain people. And also, you just can't have judder. Judder is stutter in time, just means not having a high enough frame rate across your several frames. If your frame rate is not high, then your head tracking will not be perfect. You'll have high latency on some frames, and that will feel bad to the player. Your brain understands how this stuff's supposed to feel. Okay, so let's talk about this stuff. So, at the beginning, I would say 2 or 3 years ago, we started shipping VR headsets to hobbyists and developers. We saw a lot of experimental software, like, oh, look, I took my favorite first-person shooter game and I put a VR camera on it. Now you can play it in VR. And 50% of all the people are like, well, that's cool, but I can't play it. It feels bad. And we got to the first iteration of real consumer software, about a year ago when the Rift launched. A lot of developers, in order to not make their customers feel sick, just didn't move the camera. They use a teleportation mechanic, or they built their entire game around a single position that you don't move from. And those systems work. If you're not moving the camera, there's no chance of vection. We're starting to see games that actually do move the camera, kind of the way we are used to with a traditional game, but they're getting away with it. And they're moving the camera in a way that doesn't make a large selection of people feel sick, and they're doing it by carefully designing that camera around the constraints of VR. So the most common pattern, as I mentioned earlier, is linear velocity. No ease in, no ease out, no angular rotation. This is the core piece that is common to all of the successful first-person movement systems I've seen in VR. If you're moving at linear velocity, you're automatically going to feel better to a large percentage of the population. It doesn't help everybody, but it's a pretty good start. Second is tunnel vision. This is a system by which you sort of start to block out what's on the peripheral vision, particularly if you're moving quickly or if you're moving close to something that's going to have a lot of noise in your peripheral vision. The highest quality implementation of this that I've seen is Ubisoft's Eagle Flight. Eagle Flight, you're an eagle and you're like flying through Paris, and sometimes you fly down into the ground and you're going right next to buildings and stuff, and there's a lot of motion in the side of your peripheral vision there. And what they do is they sort of pull in this little black blob to block out the your peripheral vision in the direction of some object that's close to you. And if you looked at this on the screen, like on a flat screen, you'd think that these black blobs that are sort of moving in and out of the time would be just really annoying and disconcerting. But when you play it in VR, you don't even notice. You're not focused on your peripheral vision. You're looking ahead. And it actually does a really good job of limiting that pixel flow and making the motion feel better. You can do this even with a simpler system, though. Just a dark ring that pulls in as you start to move seems to help a lot. Another thing that people are using is snap turns. These are where, instead of rotating smoothly when you click on the right stick, you just sort of snap 30 degrees. And if you look at the screen, it looks really weird to sort of snap as you're moving, but in VR it actually feels okay, and players acclimate to it really quickly. Snap turns are actually a sort of high-level version of a more fundamental idea, which is called change blindness. Change blindness is a system by which your brain is actually really good at filling in the blanks of reality all the time. Like you blink and you don't realize that you've blinked. You don't have a visual knowledge that your eyes closed and you couldn't see anything for a minute. Because your brain is actually taking in information from all sorts of different places. It's got your vestibular system and your vision and your skin or whatever, and it's trying to build this contiguous simulation of reality for you. And to do that, it has to fill in the blanks all the time. And we can kind of leverage that as we're leveraging in a snap turn here. We don't see the turn, but your brain readily believes that it's happened. Because we don't see it, we don't have a conflict with our vestibular system. We can use this basic concept for more complicated things. So for example, in VR, if you want to put somebody into a car. Like in a regular first-person video game, the way that you would animate getting into a car is, you'd come up to the door, you'd open it, then you'd slide into the car and then be behind the wheel and be ready to go. And you can't do any of those things in VR. First of all, that slide into the car, that's a curve. That's all acceleration. You're gonna feel it. It's gonna feel bad. And also, you just disconnected the player's head from their body. You can't animate the camera that way. But really simple solution to getting in the car is, get to the point where you open the door, look at the car, go to black, and then you're behind the wheel. You do this pretty quickly, and the player won't even notice that this has occurred. You just cut directly to the place where you need to be, but it's what the player expected to happen. And you denied the player and the player's brain, more importantly, information that would have maybe made them feel bad. This works really well, and we're seeing folks use change blindness as a system to sort of get through a lot of the sort of complicated motions that video games traditionally have animated without actually damaging the experience. Another first-person motion system that we're seeing a lot of is head steering. Now, this is where you use your head as a rudder. So when I'm moving, I'm always moving in the direction that I'm facing. And if I turn my head while I'm moving, then I start to move in that direction. And this gives you a much smoother sort of a way to move around the space, but because your head is actually moving one-to-one with the way your direction is moving, it doesn't trigger vection in most people. This is particularly useful for games because they have no linear velocity in their system that are just start and stop motion. On Gear VR in particular, we have a number of titles that I'm either moving or I'm not moving, and when I'm moving, I'm driving with my head, and this actually feels really good. If you're interested in this, Anshar Wars on Gear VR, which is a third-person space combat game, Affected the Manor, which is a horror game, and many others are really good to look at. They do this really well, and they're available to a very wide range of people. And on Gear in particular, you have this little touchpad on the side, which works really well for moving versus not moving. It's a primary interface for a lot of games. Speaking of Gear VR, I just want to give a quick shout out to this controller that we just shipped, Gear VR controller we shipped with Samsung. It gives you orientation and a trackpad and a trigger. It's pretty cool. We think it's actually going to change the way that Gear VR games are played really dramatically. If you're developing for Gear VR today, you should absolutely be developing against this thing. You should also keep in mind that a lot of people don't have this yet. There's a large install base of existing Gear VR users that don't have this controller. So my recommendation would be to develop, if you're going to use this, develop both for the controller and allow people to use the headset alone. It's also worth considering optional gamepad support. There aren't a ton of Gear VR users out there who have Bluetooth gamepads, but they spend a huge amount of money compared to the average person. So if you can add optional gamepad support, if your game makes sense for that, you may unlock that audience. Another common problem that we see with sort of early VR development is depth queue issues. So like in a traditional game, if you want to render your HUD or your subtitles or something, essentially the way you would normally do it is you'd render the scene, and then you'd clear your depth buffer, and then you'd render your 2D scene on top of that, so it's like an overlay. And essentially what you're doing is you're sticking all of your HUD elements to the glass on the TV or on the computer monitor that the player is using to. And that doesn't work in VR anymore. But a lot of people try it. Like the thing that people usually do is they're like, well, I got my subtitles, and I'm just going to put a quad in space. It's going to hang out there, and it'll be an overlay, but it's fine. And the reason this doesn't work is your brain is looking at that object with stereoscopic vision and can tell how far away it is. And if you've made it an overlay, probably it's actually kind of a little bit further back than it appears to be. Like, it's not sorting with depth in your scene, so it appears to be on top of things that it may actually be behind or be further away from. And because you have stereoscopic vision, you can actually tell how far away those things are. And this causes like what we call a depth queue conflict. And it's extremely common, and you should absolutely work to avoid it. It happens in reticles, it happens with text, any kind of overlay HUD. My recommendation here, the best systems that we've seen for dealing with this are to actually just stick all of your HUD elements on something physical, whether it's the inside of a physical helmet or on an arm or on the wall, or put something at depth in the scene so that there's no depth queue conflict. We also learned that spatialized audio matters a whole lot. Like, the difference between spatialized audio and non-spatialized audio in a immersive environment or in a VR environment is a really significant degree of immersion. You should absolutely spatialize all your audio. We have an SDK for this. There's many other SDKs, so it doesn't really matter what you use, as long as you have proper spatialization, where you can like close your eyes and point at where the sound source is coming from and be right. You don't need to spatialize everything. You don't need to spatialize your ambient sounds, your room noise. You don't need to spatialize your music, but anything with a physical source. If we were having this conference today in VR, the sound of my voice ideally should be coming from the speakers or from me. If I'm standing in my kitchen, I want to hear my refrigerator where it is. Anything that has a physical source, you should absolutely spatialize. This is actually a pretty easy thing to do, and it's a super huge win. Okay, so quick recap on this stuff. I'm going to move really quickly through this. I want to talk about positional tracking a little bit. Positional tracking is a technology that we use to track where your head is in space. We think, based on user feedback that we've received, that most people have about a 2.6 meter diagonal space available to them for VR in their homes. So that's about 6 feet per side if it's a box. It's probably not a box, it's probably a rectangle that extends from like a desk or something. It's different for everybody. But generally speaking, you could assume that people have about 4 square meters of total track space. That's irrespective of what the hardware is capable of tracking. This is what we think that they actually have available to them. There's also, a lot of different types of tracking that you could develop for. I mean, there's like room scale, 360, 180, swivel chair, couch play. I mean, some people, particularly if you're building for like Gear VR or a mobile headset, are going to play your game in a plane where they can't even turn all the way around. To the extent, and guess what? Like, even if you think your awesome motion control game is for standing up and running around, there's going to be players who sit down and play it. And that's fine. It's their choice. To the extent that you can allow your game to be played in different ways with different positional tracking setups, you unlock a larger potential audience. You can't stop players from putting their heads through walls with positional tracking. Like, they own the camera now. They can move the camera based on their head, and they can go walk over and just put their head right through the polygon of your wall. And often that's really bad because it looks bad, but also it may reveal information that they're not supposed to have yet. Best solution I've seen for this is games that actually fade out when you pass through a wall. And the absolute best implementation I've seen is to put a collider around the head and start to fade based on the depth of interception or penetration to the wall. So as the player starts to put their head into the surface, you start to go to black. And the nice thing, and by the time they've gotten all the way through and can see through the side, you're entirely black. The nice thing about this is a lot of players don't do this intentionally. They move a little bit wrong, or they kind of put their head the wrong way, and if they start to see that you're fading to black, they will realize that they've done it wrong and self-correct. I think Alien Isolation is the first game I saw that does this really well. There's a number of titles that do this. I want you to think carefully about where you put your camera, particularly where the camera origin is. We provide basically two camera origins, floor or eye level. If you use the floor, it means you know where the floor is. And it means when the player puts a headset on, they're their real height. They're their actual real-world height in your virtual world. And that's cool, particularly if you have things falling on the floor or you want to make it so immersive that it looks like the real world. Floor is a really common choice. However, if you choose to use floor as your origin, you probably have a much harder time rendering a virtual body because that virtual body has to be of arbitrary height. It has to be the height of the real player. So probably if you're going to do this, you're going to go develop an avatar system that allows you to scale that virtual body pretty dramatically, between the sizes that humans could be. If you choose camera, virtual bodies are easy. In this case, you just put the origin right in the player's head, and wherever the headset happens to be is the origin. You don't know where the floor is anymore, but for a lot of applications, you don't care. Now, you could give the player a completely different perspective. Perhaps I want to make you see the world from the eyes of a child. I can change your height if I use the camera as the camera position as the origin. Also, if you have a seated game, for example, if you played Eve Valkyrie, if you have a seated game, then you almost certainly want the origin to be at the camera level rather than at the floor. Because you don't actually care where the floor is. And as you can see in something like Eve, when you look down, you can see a really awesome body. It's very easy to place that there because you control the placement. I'll talk very briefly about virtual humans. I think virtual humans are, and when I say virtual humans, I mean like non-player characters that are in your world that appear to be human and interact with the player. I think they're super important. I think we don't do them very well yet. What I'd like to ask you to do is if you're building avatars or NPCs or monsters or whatever it is in your game that appear to be in the world, like make their eyes track, make their head track, do the bare minimum to acknowledge the player's existence in the world, because when you don't do that, they look like corpses. Also, I think there's a huge number of really interesting problems still to be solved related to virtual humans. This is an example from a game called Dead and Buried that we developed that is a multiplayer shootout thing. And in this case, this character is animated entirely with network information about the head and hands from a remote player and some animation magic and IK. And what's interesting about this is all we really have coming across the wire is the head and hands information, and all the other animation you're seeing here is generated in real time, based on what the system assesses this player to be doing. And as you can see, it's actually like pretty expressive, right? Like we don't have canned animations for all of these things. We are just trying to map their body position to what they probably are. And it works pretty good. This is not trivial to implement, but it's super duper awesome, and I highly recommend that particularly if you're making a multiplayer game, that you look into this stuff. Okay, cool. So let's talk about motion controls. So there's a bunch of different motion controls on the market, but I'm going to talk about our particular motion controls, Oculus Touch. And what I think is interesting about our particular motion controls is that they're designed to try to give you hands. I mean, our goal is to give you virtual hands in the virtual environment. And that changes the way that you interact with that environment pretty dramatically. Hands are also really hard to get right, and there's all kinds of super meaty, awesome problems to solve related to hands. One of the key things that we see from developers who are shipping today, building touch games, is some developers have what we call good registration, and other developers have poor registration. Registration is the feeling that when you look at your hands, your brain believes that they're your hands. You look at them and your brain's like, yeah, those are my hands. And sometimes that works, and sometimes your brain will be like, no, I don't know what's going on there, but those aren't my hands. And if you don't have good registration, then hand controls are not going to work very well from you. One of the ways we test registration is to do this back of the hand test, where we put our hand out and then we try to rub the back of our hand with a finger. And if, like, visually it lines up with what we're seeing in VR, like we can feel our finger touching the back of our hand at the point that we see it happening, then our hand registration is probably pretty good. Most hand registration problems come down to the models for the hands not being very well aligned to the actual positions of the hands in real life. Often when we do this test for a developer who's doing their first hand implementation, it'll be like this. It'll be completely off. And once you fix that, it changes the feeling really dramatically. You also want to be careful about scale and latency. You can probably get away with big hands because your brain will assume that they're gloves, but it's harder to get away with little hands. If you introduce latency to the system by smoothing, it will cease to feel like real hands and your brain won't believe it anymore, so don't do that. You don't want fleshy hands. You probably don't want realistic looking hands. These tend to look like dead hands. You can get uncanny valley of the hands, which is weird, but it's a thing. People are uncomfortable with them. If you look at Oculus's hands, they're like these blue, ghosty, ethereal things, and that's because they're hands that anybody could believe are their own hands. Like positional tracking with their head, you cannot stop players from putting their hands through geometry, and you shouldn't try. And I said that for about a year and a half, if you stop hands by, on collision, then it's going to feel like tracking is broken, and you're going to have a bad experience. Don't do that. Oculus made our little ghost hands because that way it looks like it's plausible that they could go flying through a desk or something, and players won't be upset. And I said that to a bunch of developers, and there's a couple of developers like, yeah, that's fair enough. And then there's some other developers like, I really do want my hands to collide with stuff. And they came up with a really cool solution, which I've seen in a couple of applications now. The first developer I saw to do this was Surgeon Simulator, a developer named Bossa Studios. And what they do is they have a physical hand that does collide with the world. But when that collision happens and the hand stops because of that collision, they have a second hand, which is this sort of ethereal skeleton thing, come out and continue to track the real hand position perfectly. And the nice thing about that is that the player immediately understands that tracking is not broken. Like their hands are stuck, but their ghost hands are still going. And it also communicates to the player without any sort of tutorial or anything that they messed up. They need to go back and get their hands. And it's weird. The first time you try it, you're like, well, that's weird, but it actually solves the problem pretty well. Forearms are challenging. Your brain has a system called proprioception, which means it knows where your forearms are. And a lot of people try to do arcade forearms and full arms so you can see the things. And if you get it wrong, it'll feel weird because your brain will know where your elbow actually is, and your eye system will get it wrong. It is totally possible to do well. This is a video from a game called Lone Echo, which actually gives you an entire body, including forearms that are tracked against touch controllers. But it is challenging, and it's something that you should not attempt lightly. Most folks are just showing hands for this reason. Generally speaking, anything involving motion controls that involves heaviness or torque doesn't feel good when you have hands. You can't pull a big lever like this because there's no torque. If you implement this in your game and you try to pull it, it'll feel like it's made out of styrofoam or something. It just will have no meat to it. I would just avoid sort of large object interactions like this. Minute interactions like flipping a light switch or poking a little monster or throwing a wiffle ball or something, on the other hand, feel amazing because your brain doesn't expect there to be any resistance. Similarly, two-handed operations are hard to do, like pumping a shotgun or holding a big, heavy thing with two hands are difficult to get right because there's really no resistance there. Anything that would normally require sort of a rigid interplay between your hands doesn't work so well. When you go to pick things up, the best way to pick things up is to pick them up the way that they look like they should be picked up. Like the gun is like the classic example. Everybody knows how to hold a gun, and when you go down to grab a gun, like nobody goes to grab it by the barrel, right? You all go to grab it by the grip. And when that happens, what actually happens in code is your hand gets kind of close, and they hit the trigger, and there's like a intersection test, and it's like, yeah, you got to grab it. And the question is, what do you do at that point? And for something like a gun, where it's obvious how you should hold it, you should just snap that thing right into their hand. Like they're going to grab the gun or the teapot or the cup or anything that has an obvious grip location. They're going to grab that. They expect to grab it. There's an obvious way to grab it. Just snap it in there so it's right. And that's what they expect to happen. That's what will happen. It'll feel good. For things that don't have an obvious way to hold, like a baseball or like a soccer ball, you should probably just attach the object at the exact point of intersection and have it come back with a hand. It's interesting to think about ways to do handedness, like objects that can be held in multiple ways. This is a video from a game by a developer called Tripwire called Killing Floor, and they have a knife that you can actually hold one way, or you can flip it around and hold it another way. And a year ago, we would have told you this would be really difficult to do properly in VR because we don't know how to like switch between handedness. Like once you've picked it up, how do you switch to the other side? But they just put it on a button, and it's super genius. Like it's a really simple solution, but it's obvious to the player what's going on. Once you hold it from the grip, you know you're using it like a knife. When you hold it from the tip, then you can throw it, and the throwing mechanics change. Super smart. Speaking of throwing, it's really hard. You should put a lot of time into making your throwing feel proper. We used, for Toy Box, which was our sandbox environment that we made, we used a window of velocities over some time that we then averaged to compute the throwing velocity. And we did that because we saw people would stop their hand right before release, and so that their like immediate velocity right at the point of the release was near zero, but their previous velocity had been very high. But if you really want to see how to throw things, you should look at Job Simulator. Job Simulator actually implements a different throwing mechanic for every object in the game that you can throw. The way that you throw a plate is like this, and the way that you throw a paper airplane is like this, and the systems that are running those are different for those objects because they have obvious ways to throw them. It's also important to give your players spatial cues about where their hands are, if you can. For example, drop shadows, or an intersection shader, or even turning on the rumble in the controller when they start to intersect something. Anything you can do to communicate to the player that they've now impacted the world or intersected the world is useful. Okay, so I'm going to wrap this up. Almost out of time. This is my recap for good motion controls. This is all stuff that we've learned ourselves in the last year or so, and there's a bunch more to learn. The main message I'd like you to take away from all this is super exciting and super meaty, interesting problems, but you can't take them lightly. I mean, what we have seen from the developers that are building the best things are the developers that get interested in a system and work on it until it feels good. And often that's a weird, solution that doesn't look like what we've had, traditionally in video games. So to close this out, we have a bunch more developer resources at our website. There's tools and documentations that you can ping me on Twitter if you want to. Mostly I only tweet about obscure Japanese horror games. But that's all the time I've got. I think I have 2 minutes for questions, and then we'll close this out. Thank you very much for coming.
Hello. Hi. Sounds like you've given this presentation before because that was really well done. So.
Thank you.
My question was, it sounds like you would consider some things at the moment just off limits for VR, just don't do it, like a huge lever that you would expect to be really hard to pull, doesn't feel good, non-linear, I guess acceleration at all, doesn't feel good. So I remember the early days when I had a very early Vive prototype hardware. One of the early games that people were having us test was this little circus that you would enter, and you would walk in a tightrope in one of the mini games. And if you fall off, then they have you crashing to the floor. So if you wanted to do that in VR, let's say someone wanted to do that in VR, would you just say, nah, don't do it, you can't do it?
No. What I would say is you cannot do it the way that you would have done it previously in a traditional video game. And if you go into it with the understanding that you're going to have to design it for VR, you'll find a way to do it. But the ways to do it are not the ways that we've done it previously. Like the precedent for something like that doesn't apply. In the case of falling off a tightrope, for example, if you can make that motion very, very fast, like it's over in less than a second, you might be able to get away with it. It is also on you to sort of come up with an idea and test it. One of the things that we see from early devs is, they'll put the headset on and say, it feels great to me. And that's actually kind of arrogant. Like that doesn't actually tell you anything about how your customers are going to feel. So if you have something that you haven't seen before, hasn't been done before, test it. Yes, here.
All right. The human IK, do you have samples, or are you planning to put out notes or whatnot on how you?
Sorry,
do that?
your question
the
was
human
about
IK. The human IK.
The human IK, yes. Actually, so the IK stuff that we showed from Dead and Buried was developed internally at Oculus, and we actually have a pretty significant write-up about how it works, written by the author that is set to go live in our dev vlog pretty soon, and it has those videos in there and a bunch of technical information. So I don't actually think it's live quite yet, but if you head out to our developer blog and take a look there, I actually think we'll see it pretty soon. So that is all the time I had. The little dot here is turned red for me. So I'm going to close it out here. Thank you very much for coming. If you have follow-up questions, I'll stand off to the side of the stage, or you can ping me or send me an email or whatever. Thank you very much.